ask you something. What would you say if I told you that two tiny particles, maybe, I don't know, separated by the entire universe, could be so linked that measuring one instantly affects the other, no matter the distance? Sounds like science fiction, right?
It absolutely does. It's one of those ideas that just feels wrong, intuitively.
Well, today we're diving deep into exactly that. One of the most mysterious and, let's be honest, kind of unsettling phenomena in physics, quantum entanglement.
The very thing Albert Einstein wasn't too keen on.
Right. He famously called it spooky action at a distance. You can almost hear the skepticism in that phrase.
You really can. It challenged everything we thought we knew about cause and effect, about how reality itself is put together. But the incredible thing, the really amazing part, is that this isn't just some abstract idea stuck on a blackboard anymore.
That's exactly where we're going. This spooky action, it's not just theory. It's actually starting to, well, change everything. So in this deep dive, our mission really is to unpack what quantum entanglement is. Where did this controversial idea even come from? How did scientists prove something so, well, spooky?
And then the really exciting part, how is this seemingly abstract thing driving actual real-world technology?
Exactly. We're talking things that could redefine secure communication, computing, maybe even our fundamental grasp on reality.
Yeah, so our goal here is to give you that shortcut, to get you up to speed on something that's genuinely shaping the future. We'll pull out the key insights, the surprising facts from the research.
Think it makes sense.
Hopefully, yes. Make it clear and engaging.
So whether you're maybe catching up for work or you're just like super curious about how weird the universe can be,
Which it definitely can be.
we're here to guide you through those essential nuggets of knowledge. So yeah, get ready. Things are about to get a little spooky.
In the best possible way.
All right, let's get into this origin story. It's kind of paradoxical, right?
Yeah.
We need to go back to the dawn of quantum mechanics. Now, most of the time, we live our lives by classical physics, Newtonian rules. Throwing a ball, launching a rocket.
Predictable stuff, cause and effect, you know where things are, where they're going. Everything has definite properties.
But then you zoom way, way down to the level of electrons, photons, quarks, and things get weird.
The classical rules just break down. You need a different set of rules. Sometimes it's Einstein's relativity, and sometimes, even deeper, it's quantum mechanics.
How do you think about that difference? Like different rule books for different scales?
That's a good way to put it. I sometimes think of it like a pile of sand. From a distance, it's just a pile, right? You can describe its shape, its volume. That's kind of like classical physics.
Got it. The big picture.
But get closer, and you see it's made of individual grains. Each grain has its own properties. They interact. Maybe that's like, I don't know, a bit more detail. But zoom in again, like with a super powerful microscope, and you see the grains are made of silicon atoms, oxygen atoms. That's the quantum level, the fundamental building blocks. And the rules governing them are totally different, totally counterintuitive compared to the pile of sand.
So classical physics is the pile, quantum mechanics is the atoms, different levels of description.
Exactly. And it was down at that weird atomic level that Einstein, Podolsky, and Rosen dropped their bombshell in 1935.
The EPR paradox paper.
The EPR paradox,
Yeah.
yeah. They basically looked at quantum mechanics as it was and said, hang on, is this really the whole story? Is it complete?
And their main sticking point was entanglement.
Precisely. They looked at this prediction that two particles could be linked instantaneously over distance and thought, that can't be right. It seemed to violate what they called local realism.
Okay, break that down. Local realism.
Sure. Local just means stuff can only be affected by its immediate surroundings. You push something, it moves. No action at a distance, right?
Makes sense.
And realism means things have definite properties before you measure them. A coin is either heads or tails, even if it's hidden under your hand. The property exists independently.
Okay, local effects, real properties, our everyday intuition, basically.
Pretty much. And entanglement seemed to fly in the face of that. Einstein's spooky action at a distance phrase really nails his discomfort. How could measuring particle A instantly affect particle B miles away if nothing traveled between them?
It sounds like it breaks causality or the speed of light limit.
That was the fear. It felt like it undermined the very foundations of physics as they understood it. So Einstein wasn't saying quantum mechanics was wrong necessarily.
Just incomplete, like there was something missing.
Exactly. That led them to the idea of hidden variables.
Hidden variables,
Yeah.
like secret instructions the particles carry.
Kind of, yeah. The idea was maybe the particles aren't deciding their properties at the moment of measurement. Maybe they already know what result they'll give because they have some pre-existing hidden properties like little instruction manuals we just can't see.
So if you measured their spin, they'd already agreed beforehand which way they'd point.
That was the hope. If hidden variables existed, then the correlations wouldn't be spooky action. They'd just be prearranged. Like opening two sealed letters mailed separately that contain the same message because they were written that way beforehand.
It saves locality and realism. The correlations are just correlations, not spooky influence.
That was the argument. Quantum mechanics would be correct in its predictions, but it wouldn't be the complete picture because it didn't account for these hidden variables.
Okay, so that's the EPR argument. How did that get resolved? Or challenged?
Well, it stayed mostly a philosophical debate for like 30 years until John Bell came along in 1964.
Right, the famous Bell paper on the Einstein-Podolsky-Rosen paradox.
That's the one. Bell did something brilliant. He took this philosophical argument about hidden variables and turned it into a testable mathematical prediction.
He brought it into the lab, essentially.
He paved the way for it. He said, okay, let's assume these local hidden variables exist. Let's call them A. If they exist, then measuring particle 2, let's call the result B, shouldn't depend on the setting of the detector for particle 1, call that setting A, and vice versa. Everything is locally determined.
Okay, that sounds like the local part of local realism.
Exactly. And based on that assumption, Bell derived a mathematical limit and inequality, now called Bell's inequality. It basically set a cap on how strongly correlated the measurements on the two particles could be if local hidden variables were the explanation.
A specific number, a threshold.
A specific threshold, yeah. Then he compared that threshold to what quantum mechanics actually predicts for certain entangled states, like a singlet state where particles always have opposite spins.
What did he find?
A direct conflict. Quantum mechanics predicted correlations stronger than the limit allowed by any local hidden variable theory.
So quantum mechanics and local realism make fundamentally different predictions about the world.
That's the bombshell, and Bell knew it. Right after deriving the inequality, he wrote, quite starkly, "But it will be shown that this is not possible."
Wow. So he was saying right there in the paper that the quantum mechanical view cannot be reconciled with Einstein's preferred picture of local hidden variables.
Pretty much. He showed that you couldn't just patch up quantum mechanics with hidden variables to save locality. You had to choose. Either quantum mechanics is right, and reality is non-local in the spooky way, or quantum mechanics is wrong.
That really set the stage for experiments, didn't it? It turned a philosophical debate into a question science could actually answer.
Absolutely. It was a watershed moment.
Okay, so we have Einstein's spooky action, the idea of hidden variables to avoid it, and Bell showing that, well, you probably can't avoid it if quantum mechanics is right. Let's nail down the definition then.
Yeah.
What is quantum entanglement?
Right. So putting it simply, it's this unique physical link where two or more particles become connected in such a way that they effectively share the same quantum state, no matter how far apart they get.
Sharing a state. What does that mean practically, like the coin analogy?
The coin analogy is helpful, yeah, but we need to be careful. It's not just like knowing one coin is heads means the other might be tails.
It's stronger than that.
Much stronger. Imagine these are special entangled coins. You flip yours, it lands heads. Instantly, and I mean instantly. Even if the other coin is on the moon, absolutely no, it landed tails.
Always. 100%.
For a perfectly entangled pair, yes. Their outcomes are perfectly correlated, or anti-correlated in this case. It's like they never really separated. Even when they're physically apart, they act as one unified system.
That instantaneous connection across distance is the spooky part, right? Does that mean information travels faster than light? That was Einstein's big worry.
The million-dollar question. And the answer, perhaps surprisingly, is no. No information is actually sent faster than light.
How can that be? If measuring my coin instantly tells me about the one on the moon.
Because you don't know the state of the distant coin until you measure yours. And the outcome of your measurement is fundamentally random according to quantum mechanics.
Okay.
So you measure heads. Then you know the other is tails. But you couldn't have forced your coin to be heads to send a heads message. The outcome was random. The correlation is instant, but you still need to communicate classically like making a phone call to compare your results and see that correlation. You can't use entanglement alone to send a deliberate message faster than light.
So the spooky action is the collapse of their shared state, not sending a signal.
Exactly. It highlights that crucial difference between separable and entangled states. Separable states are like normal coins. You can describe each one on its own.
Its properties are independent.
Right. But an entangled state is, well, inseparable. You can't describe particle A fully without also describing particle B. The source material puts it well. It's impossible to attribute to either system A or system B a definite pure state.
They're linked at a fundamental level. Measuring one defines the state of the other because they were sharing that undefined state beforehand.
Precisely. And physicists have specific examples of these maximally entangled states, especially for qubits, the quantum bits used in quantum computing. They're called Bell states.
Bell states, named after John Bell.
Yes, they represent the purest, strongest form of entanglement between two qubits. Fundamental building blocks for a lot of quantum information science.
Okay, so Bell set the theoretical challenge, defining the difference between local realism and quantum mechanics. The next step must have been experiments, trying to actually see if Bell's inequality was violated.
Absolutely. Bell's work lit a fire under experimental physicists. His inequality wasn't just math, it was a recipe for an experiment.
As you said, he showed that the quantum math predicted results that cannot be represented by the kind of form that local hidden variables would predict. So the goal was to measure those correlations and see which prediction reality followed.
Exactly. Does the world obey Bell's limit, siding with Einstein's intuition? Or does it violate it, confirming the spooky predictions of quantum mechanics?
And the first tests started when? The 70s?
Yeah, John Clauser was one of the pioneers, building on Bell's work. Alain Aspect followed with more refined experiments in the early 80s. They typically generated pairs of entangled photons.
Often using those atomic cascades you mentioned,
Yeah.
where an atom spits out two linked photons.
That was one common method, yes. Then they'd measure the polarization of these photons at separate locations with detectors set at different angles.
And statistically, what did they find?
Over many measurements, the correlations consistently violated Bell's inequality. They were stronger than any local hidden variable theory could explain, matching the predictions of quantum mechanics.
So score one for spooky action.
Pretty much. But there were always nagging doubts. Skeptics pointed out potential loopholes.
Loopholes, like ways the results could be explained without violating local realism.
Exactly. Two big ones were the detection loophole. Maybe the particles you didn't detect were skewing the results, and the locality loophole, maybe the detectors weren't separated far enough, or the measurements weren't fast enough to rule out some kind of hidden classical signal traveling between them, slower than light, but still fast enough for the experiment.
Ah, okay. So the early tests were suggestive, but not absolutely conclusive.
They were very strong evidence, but yes, those loopholes left a sliver of doubt. That's why the more recent experiments, the loophole-free Bell tests, are so critical.
These are the ones from the last decade or so.
Right. Teams around the world, including one led by Anton Zeilinger, designed incredibly sophisticated experiments to close all known loopholes simultaneously. They separated entangled particles, sometimes electron spins, over large distances like 1.3 kilometers. They used ultra-fast, random settings for their detectors and achieved very high detection efficiency.
Removing any ambiguity.
As much as humanly possible. And the results. They decisively confirmed the violation of Bell's inequality. The correlations are real, and they cannot be explained in terms of local hidden variables. The spookiness is real.
Which makes sense why Clauser, Aspect, and Zeilinger shared the Nobel Prize in Physics in 2022.
Absolutely. Their collective work, spanning decades, took entanglement from a philosophical puzzle to experimentally verified reality. It was a triumph for quantum mechanics.
And you mentioned something even stranger before. GHZ states, Greenberger, Horn, Zeilinger.
Ah, yes. GHZ states they take the weirdness up another notch.
How so? Even weirder than violating Bell's inequality.
In a way, yes, because they show the conflict with local realism even more directly, without needing statistics or inequalities.
No statistics. How does that work?
With GHZ states, which involve 3 or more entangled particles, you can set up measurements where quantum mechanics predicts a perfect correlation, like the outcome is always +1 under certain settings, while any local hidden variable theory predicts a different, also perfect outcome, like always manic 1, for the exact same measurement.
So a single run of the experiment gives you a result that directly contradicts local realism. not just a statistical trend.
Exactly. It moves the debate from quantum mechanics predicts stronger correlations to quantum mechanics predicts an outcome that is absolutely impossible under local realism. It's a much starker, more undeniable contradiction. A real mind bender.
Okay, my mind is officially bent. So entanglement is real, it's weirder than we thought, and it's been proven up to the hilt. But how do scientists actually make it? It doesn't just happen, right?
Right, it's not just floating around. Scientists actively create and manipulate entanglement in the lab. It's become a standard tool in quantum
Like
physics.
an engineering process almost.
In a sense, yes. A very, very delicate quantum engineering process. The most common methods involve getting subatomic particles to interact directly under very controlled conditions.
What's the go-to method?
For photons, a technique called spontaneous parametric down conversion, or SPDC, is probably the workhorse.
SPDC. Sounds complex.
The idea is reasonably straightforward, though. You take a high-energy laser photon and shine it through a special kind of nonlinear crystal.
Okay.
And sometimes, spontaneously, that single high-energy photon will split inside the crystal into two lower-energy photons.
One becomes two.
Right. And because of the way this happens, conserving energy and momentum, these two new photons fly off in different directions, but they are born entangled, usually in their polarization.
So if one is measured horizontal, the other is instantly vertical.
Or whatever entangled state you engineer them to be, and it's a very reliable way to generate pairs of entangled photons on demand.
Are there other ways besides SPDC?
Oh, definitely. Researchers are very inventive. They use things called fiber couplers to mix and guide photons in optical fibers to create entanglement. They can use quantum dots, which are like tiny artificial atoms made of semiconductor material. When you excite a quantum dot, its decay can emit a pair of entangled photons.
Artificial atoms making entanglement. Cool.
There's also the Hahn-Mandel effect, which is a beautiful quantum interference phenomenon that can be used to prepare certain entangled states. And even more exotic stuff, like using Hardy's interferometer setups to entangle a particle with its antiparticle, like an electron and a positron.
Wow. Particle-antiparticle entanglement. The scope seems huge. Has entanglement been seen in, like, really big or complex systems?
It's definitely moving beyond just pairs of photons or electrons. As you mentioned, entanglement's been observed between top quarks at the ADALAS detector at CERN.
Top quarks. Those are heavy hitters in the particle world.
Extremely massive and very short-lived. Detecting entanglement there is happening at incredibly high energies, pushing the frontiers.
And what about larger scales? Not just fundamental particles.
That's happening too. Scientists can now create and control entanglement between whole molecules trapped in optical tweezer arrays using lasers to hold and manipulate individual molecules. And perhaps one of the most surprising results is observing entanglement persist, even if fleetingly, in macroscopic diamonds at room temperature.
Diamonds at room temperature. I thought quantum effects needed things to be super cold and isolated.
Often they do, because heat and environmental noise tend to destroy fragile quantum states, like entanglement, a process called decoherence. But finding ways to create and observe entanglement in warmer, larger systems is a huge area of research. It shows entanglement isn't just some microscopic, low-temperature curiosity. It might be more robust than we thought.
Okay, that's genuinely mind-blowing. From a paradox to lab-made entanglement in diamonds. Now let's bridge that gap. How do we get from this fundamental, spooky physics to actual technology? People like Anton Zeilinger were key here, right? Taking the theory and making it practical.
Absolutely. Zeilinger and others were pioneers in not just proving entanglement exists, but asking, okay, what can we do with it? This really launched the field of quantum information science.
And maybe the most famous application, the one that grabs headlines, is quantum teleportation.
Right, teleportation. But we need to manage expectations here. It's not Star Trek's beam me up, Scotty.
No beaming people around. Shame.
Not yet, anyway. In 1997, Zeilinger's group did the first experimental demonstration. What they teleported was the quantum state of a particle.
The state, not the particle itself.
Exactly. Imagine you have particle A, whose quantum state you want to teleport, and an entangled pair of particles, B and C. You send particle C to the destination. Then you perform a special joint measurement on particle A and particle B. This measurement tells you something about how A and B were related, and it destroys the original state of A.
Okay, the original is gone.
Right. Then you send the result of your measurement, just classical information like a few bits, to the destination. The person at the destination uses that information to perform a specific transformation on particle C. And voila, particle C is now in the exact state that particle A used to be in.
So the information, the quantum state, jumped from A to C without physically moving A.
Precisely. And crucially, this relies on something called the no-cloning theorem.
Ah, we mentioned that. You can't just copy a quantum state.
You cannot make a perfect copy of an unknown quantum state. It's forbidden by the laws of quantum mechanics. So teleportation is the only way to move an unknown quantum state from one place to another because the original is destroyed in the process.
That raises some deep questions about information, doesn't it? If you can move it but not copy it.
It really does. It changes how we think about information itself. And it's not just a curiosity, it's seen as vital for future quantum computers and quantum networks, moving quantum information between processors or across links.
Which brings us to entanglement swapping and quantum repeaters, building that quantum internet.
Exactly. If teleportation moves a state, entanglement swapping, which Zeilinger's group also pioneered around 1998, moves the entanglement itself. It allows two particles that have never interacted directly to become entangled.
How does that work? Like a relay?
Kind of. Imagine Alice has particle 1 entangled with particle 2. Bob, far away, has particle 3 entangled with particle 4. Now, if someone in the middle performs a joint measurement on particles 2 and 3, the inner particles, particles 1 and 4, the outer ones, held by Alice and Bob, suddenly become entangled with each other.
Even though 1 and 4 never met?
Even though they never met, the entanglement has been swapped onto them.
Okay, why is that useful? Why not just send an entangled particle directly?
Because quantum states are incredibly fragile. Send a photon through an optical fiber and it's likely to get lost or absorbed or have its quantum state scrambled, decoherence, after just a few tens of kilometers. And you can't just amplify it like a classical signal.
Because of the no-cloning theorem again. Amplification involves copying.
You got it. So direct transmission over long distances is basically impossible. That's where quantum repeaters come in.
Using entanglement swapping.
Yes. They break a long communication line into shorter segments. They create entanglement within each short segment where it's less likely to degrade. Then they use entanglement swapping at the junctions between segments to stitch the entanglement across the whole distance.
So you link segment 1 to segment 2, then 2 to 3, and so on, until Alice and Bob at the ends share an entangled pair, even though no single particle traveled the whole way.
That's the concept. It allows you to establish entanglement over potentially vast distances, forming the backbone of a future quantum internet.
A quantum internet. It sounds amazing, but how far away is it? What are the big challenges?
Well, it's definitely still in its early stages. The biggest challenge, honestly, is cost and complexity. Building these quantum repeater nodes requires incredibly specialized, expensive hardware. We're talking cryogenic cooling systems to get things near absolute zero, ultra-stable lasers, single photon detectors, precision optics. It's pushing the limits of engineering.
Not exactly off-the-shelf components.
Not at all. And maintaining it all is complex, too. So right now, building even small-scale quantum networks is a multi-million or billion-dollar endeavor.
And you mentioned standardization earlier. That's still an issue.
It is. Different research groups and companies are using different physical systems, trapped ions, superconducting circuits, quantum dots, diamond vacancies, and different protocols. Getting them all to talk to each other reliably is a huge challenge. We need common standards, like we have for the classical internet, TCP/IP, etc., before we can build a truly global, interconnected quantum network.
So lots of investment needed, lots of technical hurdles.
Billions are being invested globally. US, EU, China are all pouring money into quantum initiatives like the EU's EuroQCI. The potential is seen as huge, but yeah, it's a long road, likely decades, requiring massive investment.
Okay, let's shift to another major application. Security. Quantum key distribution, QKD. You said the security comes from physics itself.
That's the beauty of it. QKD provides intrinsically secure cryptographic key distribution. The security isn't based on assuming a math problem is hard to solve. It's based on fundamental quantum principles.
Like the no-cloning theorem again.
And the act of measurement itself. The idea is Alice sends Bob a secret key encoded in the quantum states of single photons, like their polarization. If an eavesdropper, Eve, tries to intercept and measure those photons to learn the key,
She inevitably disturbs them.
exactly. The very act of measuring a quantum state generally changes it. This disturbance introduces errors into the transmission that Alice and Bob can detect by comparing a subset of their key bits over a public channel. If the error rate is too high, they know someone was listening, and they discard the key and start over.
So eavesdropping is inherently detectable. You can't listen without leaving footprints.
Precisely. It makes the key exchange secure against eavesdropping, guaranteed by the laws of physics. It doesn't make the encryption itself unbreakable. You still use the key with a standard algorithm, but it ensures the key itself wasn't compromised during distribution.
And this is being done in practice, over long distances.
Oh, yes. Zeilinger's group demonstrated it over 144 kilometers between the Canary Islands years ago. And China's Mischief satellite achieved intercontinental QKD over 1,200 kilometers, showing the potential for global satellite-based quantum-secure communication.
That satellite work is amazing. It really changes the game for global security. How does that change our trust in tech, knowing physics guarantees the security?
It's a fundamental shift, and it gets even better. Remember those loophole-free Bell tests?
Yeah.
They form the basis for something called device-independent QKD.
Device independent, meaning
Meaning the security is guaranteed even if you don't trust the devices Alice and Bob are using, even if the manufacturer put in backdoor. As long as the observed correlations violate Bell's inequality sufficiently, the derived key is secure, regardless of the internal workings of the hardware. The security comes purely from the observed physics, not from trust in the device's design or manufacturer.
that's incredible. Trustless security based on fundamental physics. Mind blown again.
It's a powerful concept. And those Bell tests have another crucial security application, generating truly random numbers.
Right, you contrasted this with the pseudorandom numbers our computers usually generate.
Yeah, pseudorandom numbers come from deterministic algorithms. They look random, but if you know the algorithm and the starting seed, you can predict the entire sequence. They're not truly unpredictable.
But quantum measurements are.
According to standard quantum mechanics, yes. The outcome of measuring, say, the polarization of a photon prepared in a superposition state is fundamentally probabilistic. There's no underlying deterministic process, no hidden variable dictating the outcome. It's inherently unpredictable.
And verifiable, too, you said.
Using Bell tests, yes. The violation of Bell inequalities can certify that the outcomes are genuinely random and not predetermined by some hidden classical process. This gives us quantum random number generators, or QRNGs.
Which are crucial for things like generating encryption keys.
Exactly. If your encryption keys aren't truly random, they could potentially be guessed or predicted, compromising your security. QRNGs provide a source of randomness rooted in fundamental physics, essential for robust cryptography and many other applications like scientific simulations and secure lotteries.
Okay, secure communication, true randomness. What other weird applications does entanglement enable? You mentioned pictures from a paradox, quantum imaging.
This one is really cool, yeah. In 2014, a team demonstrated they could take an image of an object using photons that never actually hit the object.
Wait, how do you image something with light that doesn't touch it?
Using entanglement, they generated pairs of entangled photons. One photon from each pair, let's call them the object photons, was sent towards the object, while the other photon, the imaging photon, was sent towards a camera. Now, only the object photons interacted with the object, or didn't if the object wasn't there. But because they were entangled with the imaging photons, the information about whether the object photon passed through or was blocked was encoded in the correlations between the pairs. By cleverly measuring only the imaging photons and correlating them, they could reconstruct an image of the object.
So the camera saw photons that never went near the object, but still formed an image of it. That's wild.
It is. It's called quantum imaging with undetected photons. It allows you to image things in situations where the light needed to interact with the object might be harmful, or where your camera isn't sensitive to the wavelength that interacts best with the object.
Like that infrared example, using visible light cameras to see infrared images.
Exactly. You entangle visible photons, which your camera can see, with infrared photons, which interact with the object but your camera can't see. The visible photons carry the image information via entanglement. It opens up entirely new possibilities for imaging across different wavelengths and in sensitive environments.
From security to imaging. It seems entanglement touches everything. What are the really big questions, like time and gravity?
Ah, the deep end. Yes, entanglement might even hold clues to some of the most profound mysteries in physics, like the problem of time.
The conflict between quantum mechanics and general relativity's view of time.
That's the one. Quantum mechanics often treats time as a fixed background, a universal clock ticking away. But general relativity tells us time is dynamic, it's part of space-time, warped by gravity, relative to the observer. How do you reconcile those?
Seems possible.
Well, some physicists, like Page and Wooders back in the 80s, proposed a fascinating idea involving entanglement. They suggested that maybe the universe as a whole is timeless. Its overall quantum state doesn't evolve.
The universe is static, but things clearly happen, time passes for us.
Right. Their idea was that time emerges for observers inside the universe due to entanglement. If you consider a system evolving, like a clock, and an observer watching it, their entanglement creates the perception of time passing for that internal observer.
So the universe is timeless globally, but time emerges locally from the entanglement between subsystems.
That's the gist. It suggests time isn't fundamental, but an emergent property arising from the quantum relationships within the universe. It's a radical idea, but it offers a potential way to resolve the problem of time. If time itself emerges from entanglement, wow, that really changes our whole picture of reality.
And maybe space-time itself, too. You mentioned that briefly.
Yeah, it's an even more speculative but incredibly exciting area, often connected to ideas like the holographic principle and string theory. It's the notion that space-time itself isn't fundamental, but emerges from the entanglement patterns of quantum degrees of freedom living on some kind of boundary, potentially at a lower dimension.
Like space-time is woven from entanglement.
In a metaphorical sense, yes. The geometry of spacetime could be a reflection of the entanglement structure of the underlying quantum system. It's highly theoretical, deep at the intersection of quantum gravity research, but it shows just how fundamental entanglement might be to the very fabric of reality.
Okay, we've gone from spooky action to the fabric of space-time. Let's pull back a bit. What's the road ahead? Are we on the cusp of a quantum revolution? Or are those hurdles, cost, standardization still pretty high?
The hurdles are definitely still high. As we said, the cost is significant. Building quantum networks, fault-tolerant quantum computers, it requires immense resources, specialized materials, extreme conditions. Billions are being invested, but it's still early days technology-wise. We need breakthroughs in engineering and material science to make it more scalable and affordable.
And that standardization issue needs solving too, right? Getting different systems to talk to each other.
Absolutely. Without common protocols and interfaces, progress will be slower, and building large integrated systems will be much harder. It requires a lot of collaboration between research groups, industry, and standards bodies.
But despite those challenges, the potential payoff is just huge.
Immense. Quantum entanglement isn't just a curiosity, it's a resource that can genuinely change our present and future. Think about it. Quantum cryptography for unbreakable security, super dense coding to transmit information more efficiently, and fundamentally, entanglement is the engine that will power quantum computers, allowing them to tackle problems currently impossible for classical machines.
Solving problems in drug discovery, material science, finance.
Exactly. Simulating molecules for new medicines, designing novel materials, optimizing complex systems, breaking current encryption. The potential impact across industries is transformative. That's why there's such a global race to develop these technologies, despite the challenges.
What an absolutely incredible journey we've covered today, from Einstein scratching his head about spooky action to Bell proving him wrong, experimentally speaking.
To people like Zeilinger turning that weirdness into concrete tools and technologies like teleportation and QKD.
It really shows how fundamental physics, even the really strange parts, can end up reshaping our world in completely unexpected ways.
It really does. So hopefully you listening now have a much clearer picture of entanglement, this concept that's not just mind-bendingly weird, but is actively being harnessed to build the future.
You're definitely better equipped to understand the headlines about quantum breakthroughs now. But let's end with a final thought, something to chew on.
Okay.
If entanglement means particles can be linked across vast distances, instantly connected, acting as one, does that hint at something deeper? Could it mean the universe itself isn't just a collection of separate things, but maybe a single, vast, interconnected quantum system? A fundamental unity we're only just beginning to glimpse through this spooky action.
That's a profound question to ponder. Does entanglement point towards a more holistic reality than our everyday senses perceive?
Something to think about until our next deep dive.